All right, so good. So happy Friday. Today the plan is to comment about the last um, thing or two on the homework review because we ran out of time last time. And then I'm going to I'd like to spend the bulk of the time today on the adversarial search assignment, some mind space ideas wrapped up in that. But I'm not going to give you code, right? That's your job. But I've decided to have some empty function braces, and then I'll comment about some of the observations that are important when you're doing these implementations. Okay. All right. So where we left, written exam number one. We're going to have a review on Thursday, and it's going to be, excuse me, in class on Friday. And to those who have requested accommodations, I've received all of the accommodation letters now. So those folks are all set. I will be, or have rather, just before, earlier today, contacted the accessibility office to set up proctoring for those individuals. So I'm going to walk over there probably later this afternoon. I have a couple meetings, and there's one person that I owe a meeting to. I don't want to say your name on the recording, but if you have time, you know what I'm talking about, right? If you have time, I have an appointment at 1:30 that should take about an hour. I can stick around if that meets your schedule so we can chat about stuff. No is a perfectly fine answer too, right? So it is last minute. Whether you know it or not, you know how the proverbial sausage gets made. All of the planning for the classes to be offered, both in the fall as well as the following spring, 2027, that gets done now, right? By chairs and faculty, right? So a bunch of the trading happens and all of the determination about what have we offered or we're going to offer. And so things are a little bit busy at this juncture. Um, so the exam is going to be in class, and I've decided to make it closed book written exam, not digital, which is a scary prospect for me. But I will allow you one 8.5 by 11 sheet of notes. And so this modality affords me, especially with the large class census, the ability to ask different types of questions, things that I believe you can address in a 75-minute section, minus the 10 minutes or so that I usually take to go over the questions to make sure everyone understands the question. Because I understand that, you're all seeing this information for the first time. I saw this information for the first time a long time ago in grad school. And so something that might seem clear to me might not seem clear to you. So I always go over questions for that reason. And so I really want you to focus on understanding the concepts and the relationships between different methods. And part of my purpose today in going over the mind space of the solutions to adversarial search, which is due on Wednesday, is to have another instance of where you can see this idea of the relationships between things. Okay? All right. Any questions? No? No, keep in mind, this is the worst type of modality um, uh, for exams that I like, but it makes it easier to manage the class census. I think going forward, we're going to cap this course with a hard cap and try to offer it more, but cap it less so that we can do more interesting things with a smaller class size. All right. What else? And then the spring break after that. All right. So, yay. All right. And you won't get work from me over spring break. That goes back a long time ago. For those of you who've had other classes with me, it goes back to when I was a student and got lots of work over break, Thanksgiving in particular. Um, and so I said, one day, if I'm ever a professor, I'm not going to have work over break. But I can't vouch for my colleagues. Some of them use it as an opportunity to load you up. But that's just my philosophy. You're working hard, you've earned that, that's your time. from my perspective. All right. So we talked about a bunch of things about reachable state space. And one of the things I felt important to point out, when you talk about reachable state space is not the same as the search tree, right? Searches terminate in terminal nodes, but state space has states that are connected in some graph. So one of the things to really pay attention to is the wording of such a question, making sure you understand the distinction between the search tree and the state space, right? The search tree you can think of as being something that's induced from the state space, but the basic connectivity of the state space are all the interconnections that you go from one state to the next. So that's really important to remember in the mind space of any question. Okay? Any questions? No? All right. So let's go forward. And when you make comparison between breadth first search and depth first search, it's kind of nice to state a priori what your convention is about how successors are expanded. And it doesn't really matter what order it is. And in this case, you could say north, south, west, east, north, south, east, west. But it's nice to have the same convention for breadth first search and depth first search, because what you'll find, depending on the geometry of the environment, excuse me, you might find different behaviors. And in any sort of comparative, quote unquote, experiment, even this and simulation, you want to make sure you're controlling and for the same factor, right? And so with this, you don't want to vary the order of the successors as well as how you pick stuff off the frontier. You want to keep the ordering of successors the same for depth first search and breadth first search. And the only thing that you're varying is that selection discipline for how you pick frontier nodes off the frontier. Does that make sense? So always assume the same convention, because you're going to get varying results just from serendipity and how the goal is arranged. Okay. So let's see. The other question, and this is kind of where we hardly left off. We did the A-star search, and make it easy on me, please. When you do your A-star search, I know 1 + 5 is 6, but it's helpful to tease apart the G of n and the H of n, right? It's a lot easier to see what's going on rather than you assuming I know what you intended, right? So it's very useful to decompose it into its constituent components. And it also, to be honest with you, it's an opportunity for partial credit should you have mistakes in there, right? So make it easy for yourself and decompose that so that, it's easier to see what's going on, okay? Any questions? All right. And so admissibility and weakness, right? Please remember the definition of admissibility. And admissibility, it's a relationship to finding optimal cost paths, right? So any admissible heuristic will do it. But this idea of domination is an important concept. And so we saw consistency, that triangle inequality is an even stronger guarantee, but just remembering that consistent heuristics are admissible, but that's not always the other direction. Admissible heuristics are not always consistent. All right. Does that make sense? And when you think about this idea of domination, think from the perspective, excuse me, of the contour, the search contour projecting forward through your state space as you expand your search tree. Does that make sense? Yeah. All right. So then we left off with this one and kind of rushed through it. So I'll habituate a little bit more in this opportunity. And in this example, we have a simple maze. It's open, no walls. And we have 4 food pellets. And the question asks why, excuse me, is position alone insufficient state? And so we motivated this by going back to what our definition, excuse me, of state is. And it's all of those descriptors or aspects of the environment that are, and this is the important part, relevant to solving the problem, arriving upon a solution, transforming your initial state into a goal state, right? And so you could have different search problems where the state might be different for the same state space or the same environment, I should say more correctly. And so in this case, we said position, yeah, it's important, but it's not the only thing because position can't tell us about that part of the environment that's really critical to the goal configuration and that and that excuse me and that one of those days. And that is the eat status, as we've been calling it, of the food pellets. And so the food pellets absolutely occupy an XY position in the environment. Okay. But it's not just the XY position, it's also whether or not the pellet in those XY positions have been eaten. And so it's not enough to say Pac-Man is in some position. And if it's in a position coincident with the position of a food pellet, yeah, certainly by the dynamics of the game, Pac-Man will eat the pellet, but you don't know the status of the entire game because the state should be descriptive of the entire environment, not just part of the environment. And so we saw this with the food search problem in Pac-Man in the search project, project number 2, and we included a vector, and that vector was true if a pellet was uneaten. And so this gives us the basis of a goal check because we know we've arrived upon a terminal state in the search tree if this vector is all false. And moreover, because for this search problem, we only have 4 pellets, right? You can just designate position 1 in that 4 tuple, position 2, 3, and 4 refers to a specific pellet. So you can always update this based on the dynamics of the game, but you need an encoding of this aspect of the environment because the whole point or goal or purpose of this particular search problem is to be able to consume all the pellets. So you have to have information about the pellet consumption, however you choose to do that. Does that make sense? And so part of the focus here is really paying careful attention to what the definition of state is. And it's those relevant aspects. The same environment, different problem might have different relevant descriptors that collectively comprise your state. Does that make sense? All right. Okay. And so with that, it asks in 5B to give 2 distinct states with the same position. And so if we had Pac-Man in position, and it doesn't matter what position it's in really, let's say the current position, 1, 2, 3, 4, 5, that looks like, let's call it 6, and 1, 2, 3, 6, 3, 6 comma 3. Okay. If you had 6 comma 3, and let's say at the outset, none of the pellets were eaten, collectively, let's call this one version of our state. Collectively, none of the pellets are eaten. Well, we could still have Pac-Man in position 6-3, and maybe the first pellet, upper left-hand corner, by my convention, is eaten, and its respective position in that Boolean 4 tuple is false, but the position remains the same. And so in that case, Pac-Man might have gone and navigated to that pellet, eaten the pellet, and then for whatever reason returned back to position 6-3. Does that make sense? And so in that case, you can even tell, gosh, well, position alone is not suitable descriptor for state because these 2 configurations are entirely different, right? And the behavior is going to be different as you search as a result of that, because going in a path or making moves that advance you back to that pellet in the upper left-hand corner is not going to be fruitful, right? So you need that aspect of the environment in your description of state. Does that make sense? So really, really important is going to be this definition going back to first principles of what state is and what a search problem is. Does that make sense? All right. Any questions? No? All right. So explain why the closest food heuristic is admissible but weak, right? And so here, let's say Pac-Man, I'm going to kind of cross that out, ignore that. Let's say Pac-Man is right here, right? Now, if you had the closest food heuristic, well, that will give you a score that represents some pellet that is uneaten. Okay, that's great. But it doesn't tell you anything about ultimately getting to that goal configuration where all the pellets are eaten. And by nature, and we saw this when we looked at material costs, when we used the Manhattan minimum spanning tree, and then we had a version of the closest neighbor Manhattan minimum spanning tree where we could turn up the number of nodes that are added to this spanning tree. Now, of course, here, if you looked at the distance to the closest food pellet, absolutely, it's an underestimate of distance to the goal. But in this particular case, we have none of the pellets eaten. That'll account for that closest pellet being eaten, but it says nothing about the estimated cost to getting all of the pellets eaten, right? So again, yes, it's admissible because it's an underestimate. Getting to the closest pellet is a subset of getting to all of the pellets. Does that make sense? And so you could actually prove, based on the definition of closest and how greedy minimum spanning tree algorithms work, you can actually prove that if you add the other pellets to consideration to this idea of distance to the goal, estimate of distance to the goal, that you're going to get domination. Does that make sense? So this is just really getting you to focus on what admissibility means, but what this idea of domination, weak and stronger heuristic means. Any questions? No? No questions. All right. So that was the last question. Let's spend most of our time, I'm going to bring down the slides, in the adversarial search problem considerations. And I want to make sure I brought up the right one. I'm going to share my desktop so I don't have to worry so much about, no, I didn't want to do that. Stop. Let me try that again. Desktop. There we go. Okay, so I'm sharing my desktop. Let me minimize that. And I have PyCharm up already. And I have stubbed out some things in my own implementation. And I'm first going to bring up an example of solution. Um, Q, let's see, the first one, the second one. Oops. Oh, that's weird. That's not supposed to happen. Let me do this. Oh, you know what I did on my workstation? Oh, all right. I'm going to have to mute this. Stop. Or to the cloud. I'll just have to trust that it's there. All right. Otherwise we won't have sound. So let me share the desktop again. I'll unmute. Okay. So this is the minimax question, which is question 2. And, you know, when you think about these, you can see it does a decent job, but it kind of pauses a little bit because these are random ghosts, right? Okay, but oh, that's not the right one. All right, let me just focus on the code. Trust me that it all works. But anyways, so we start out with minimax, right? The other solutions are directly related to minimax. And so one of the things I had mentioned in our last lab exercise is to do yourself a favor and to write these helper routines. I really like to have things try as closely as possible. You can season to taste, but try as closely as possible to mimic the pseudocode. And so with that, I haven't shown you the implementations of them, but I have some stubs that are important mirroring to the implementation that mirror the example, the pseudocode. And so to move, we saw in the pseudocode, it selects or identifies who's going to move, namely min or max. And that's based on the agent index. Now, the agent index is an implementation detail because that's how the Pac-Man environment identifies which agent is going to move. And so when you do that, I like to have it return a string, min or max, and then I use that throughout the implementation because it looks a lot like the pseudocode. So depending on the agent index, you're going to identify who it is, keeping in mind that max is always the Pac-Man, right? And the Pac-Man always has agent index of 0, so-called agent 0. But also make sure that you understand that the ghosts are anything that's not agent 0. And you can have 1 ghost, 2 ghosts, 4 ghosts. It's a tunable parameter in the classic maze environment, okay? So please keep that in mind. So then there's the terminal node check. And in that terminal node check, in this particular project component, you can have a depth limited search. And so the halting criteria for determining in your search tree what is terminal also depends on the depth, not just whether you have reached an ending state or state that describes an end of the game. And so the end of the game is either that you won the game, you've consumed all the pellets, or you've lost the game, you've collided with a ghost before being able to eat all the pellets, right? And so this just helps you to abstract a little bit one level of indirection, and it also helps with a translation, so to speak, of the pseudocode. All right, any questions so far? No questions? Okay. And so then another useful routine, and you could certainly implement it differently, is result, right? And which is exactly mentioned in the pseudocode. And result is going to, these all take the game state, but it's going to return the successor given two things: the current state, which is the game state instance that's passed in, and the action that you're trying to take in that state. And so this is just going to ask the game state, what is the valid successor? What is this S prime that you get to by calling action A or performing action A in state S? Does that make sense? All right, so everything's given to you. And then actions. What is an admissible action? Certainly in the Pac-Man environment, you have north, south, east, and west available to you. It's another method in the game state or through the game state that you can arrive upon. Okay, so then there's the utility. The utility is just your eval function. It's just a straight call. And as we saw last time, you can improve upon the eval function. And there's another improvement for this assignment that we'll allude to towards the end of all this. Okay, and so did you need to have a utility method? No, you don't. But it helps when you're reading the pseudocode if you try to mirror stuff to get some of those little nuances that might bite you. And of course, even in my own implementation, I've been able to, get 100 consistently. There are some nuances that I'm trying to point you around, hopefully to help you in your thought process. And then this one, next player. Now, this next player advances a value, and that value corresponds to whose turn it is next. Now, of course, if you only have the Pac-Man, all right, no ghosts, it's pretty simple. It's just, agent 0. If you have the Pac-Man and 1 ghost, it's still pretty simple. But the thing to pay attention to is when you advance the notion of who the next player is by the agent index, you want to make sure that you don't assume you only have 1 ghost, right? You want to ask the environment how many ghosts you have, and you use that when you advance this notion of next player. And so if you have 1 Pac-Man, well, you always have 1 Pac-Man. If you have Pac-Man and 1 ghost, there's a total of 2 players. Pac-Man and 2 ghosts, there's a total of 3 players. So if you're going to use something like modulo arithmetic, make sure that you don't make assumption on how many agents exist in that instance of your environment. Okay. Any questions? No? Because part of this, one of the tunable parameters in the Pac-Man game is that you can specify how many ghosts that you have, right? Now, I haven't played with that. I don't suggest you do. Just take whatever the tests are, where it has one ghost or four ghosts and things like that. Save that ghost test for later, right? Focus on the task at hand. All right. So then I like to have a single entry point, and that single entry point I call minimax. And that's where it all starts. And the assumption is that agent zero goes first, right? Agent is always the max player. And then what I do is I use this entry point to decide which player is going to move. So I call to move here. That's just what I've chosen for my implementation. And so I can either from minimax called max value, which is max's decision, which is the Pac-Man, or I can call a method I call min value, which is a ghost's decision point, right? And so each time when I decide I'm the max player and I'm going to make a min call, I don't make a min call, I make a minimax recursive call. And then that minimax recursive call makes the right choice to call max or to call min. Does that make sense? Now, you could absolutely, there's nothing wrong with just starting with the max call here, and then the max call calls the min, and the min calls the max. But I just found it useful to call to move in this entry point and not mix that to move inside of the max action and the min action. Does that make sense? So then we have max value, and in max value, iterate over the state's admissible actions. And for each admissible action, I get the successor, and then I make the recursive call to minimax. Now, one of the considerations is that when you make the recursive call, before you make that recursive call, you have to increment to the next player, right? And so I advance the increment to the next player, make the recursive call up above in minimax. I pick out whose turn it is, whether min or max, and then I call in again. Does that make sense? Any questions? No? And so this is going to be, well, and then min value, forgot about that. You iterate over all the admissible actions, you get the successor state given that action, and then you make the recursive call to minimax. And so inside of min value and max value, I'm just using the utility of routines that we went over just a few moments ago, okay? And so you're going to spend, excuse me, most of your time on the first one, on the minimax, right? The first recursive one, because everything else that follows is kind of a special case of that. And we'll talk a little bit about those special cases, what those relationships are. Okay? And any questions? No questions? See if I see past the second row. No, all right. Okay. So then with get action, all I do with get action is I just call into minimax, right? I initialize the agent, index to agent zero, and I call minimax, and it all just happens beautifully. Any questions? No? So the next one is the alpha beta agent. And you'll notice these helper routines are exactly the same, right? They're exactly the same, except for the entry point for alpha beta search, as well as Max's choice for alpha beta search and Min's choice for alpha beta search. And where those three methods are different is that they take parameters, payload, if you will, of the alpha value and the beta value, right? So you can think of alpha beta as minimax, but what alpha beta adds to the behavior, yes, it makes the recursive call, it's max's action, recursive call, min's action. But what it does differently, it asks the question, can I improve on the floor or can I improve on the ceiling? And using that notion of improvement as through the successors, you're constantly preferring nodes to pursue that give you that improvement. Otherwise, you cut early, therefore pruning those things that don't improve the ceiling and the floor. Does that make sense? And so one of the things, well, let me just go over. I'm not going to go over the helper routines. And so I started and some recommendation. Once you have the minimax working, literally copy all the routines that you have for minimax, change the names of min's action, max action, and the entry point, and then add on to the method's signatures to add the alpha and the beta for those three entry points. So that's your starting point. So then in the business end, where you iterate over the successors, you add that admission test that says, will this successor improve upon my floor if I'm min, or improve upon my ceiling if I'm max? So it's exactly minimax, but it includes this alpha beta, and it cuts early if something fails to make an improvement. If it does make an improvement when you iterate through the successors for each of the admissible actions, then you go ahead and you update your notion of what the best value is, and then you continue to search. That makes sense? All right. So here, I won't go over all of the helper routines. And my entry point, I call it alpha beta search. Now, of course, you could just, start at max and then do the recursive call. But again, I like to have a particular entry point. And in this particular entry point, I've made the decision to call to move and call min's action or max's action as appropriate. Right now, you don't have to do it this way. It's just seemed to me, when you look at the pseudocode, having it close to the pseudocode, and there are some nuances too with this, well, I'll allude to, but having it close to the pseudocode really gets you to see these relationships between all of these approaches. Okay, all right. Any questions? No? All right. So again, we have max value. And so this is max's action, and we're going to iterate over the admissible actions, getting the successor state, and then going to make a recursive call to minimax again. But in this case, we have the pruning action. When we search over the successor states, we're asked the question, does this improve our ceiling? And if it doesn't improve the ceiling, you don't take it. If it does improve the ceiling, then, I'm sorry, the floor for max. You call it alpha beta, but you could think of it as maxi-min so that you don't confuse what the floor and ceiling is. And if it doesn't improve the floor, then you don't take it. If it does improve the floor in max's action, then you do take it, right? And use that as the updated basis for whether or not you're going to admit a particular pursuit of a particular successor node. Does that make sense? All right. But keeping in mind, like we saw in minimax, in alpha beta search, if you're going to make that recursive call before you do it, because you're pursuing a successor, you need to increment to the next player, changing the index, because the successor of a max is a min, and the successor of a min is a max. So this is, again, it's just like minimax, only this version has this notion of a floor and a ceiling, and it's trying to look for not just a successor node recursively, it's looking for successor nodes that improve the floor in the max case, or improve the ceiling, make it smaller in the min case. Does that make sense? And so literally you start by just copying your minimax solution. You change the names because it's alpha beta, add the two parameters of the alpha value and the beta value for those three routines, the entry point, max's action, and min's action. Does that make sense? Okay. So let's go down and we'll go to expectimax. And this is going a lot faster than I budgeted for. Now, with expectimax, copied alpha beta code, changed some names, kept the same helper routines, and then I removed the alpha and the beta parameters on those three methods, namely the entry point, max's action, and min's action. And so expectimax is just like alpha beta pruning. This version, nuanced difference, is it's certainly not going to look at this notion of improving the floor or improving the ceiling, right? It does something else. It looks at these expectations. And when you look at this implementation, trafficking in expectations, the whole reason for chance node, because it's kind of wonky, right? If you have two move, tell you I have a min node, I have a max node, or a chance node, it's kind of hard to do, right? And you might think, gosh, well, let me do modulo 3 arithmetic. Well, that's going to break, right? It breaks miserably. And so with this, if you think about the whole purpose of a chance node, right? A chance node is only there so that Max can consider the suboptimal moves or the random moves of min, right? And so in this case, thinking of it that way, these chance nodes are really linked to min nodes, right? And so when you're alternating, picking between max, it's your turn, and other agent, it's your turn. If you treat the other agent as a chance node and then let the chance node perform the min action, then you only have two things to pick between and not have to try to implement a wonky modular 3 arithmetic when trying to determine which version of things to call. Does that make sense? Any questions? So that's a really key insight because initially, admittedly, in my own implementation, I started out saying, "Let me have three different nodes," and then say, "Wait a minute, this feels like you're doing some kind of weird yoga, trying to put your heel behind your ear, under your neck, or something like that, right?" Which flexible people can do. But nonetheless, think of the purpose of a chance node. Its only reason for being there is to allow Max to reason over a bunch of min nodes. So treat the two agents as a max node and a chance node. Does that make sense? Because in this chance, right, in this expectation, it's an expectation over successors, but it's an expectation over successors that are always min nodes. So you only really need to distinguish max versus chance. Does that make sense? Any questions? No? All right. So here for expectimax began literally by copying the solution for alpha beta and then remove the alpha and the beta and remove the checks for greater than, equal to, less than, equal to. And then added that third routine, the expectation. And inside of the to move, I only have two conditions, one for the max and one for the chance, because the chance, by definition, its successors are going to be mins. Okay. All right. Any questions? No? All right. So here it's the same helper routines. The only difference is that the to move is going to be different. Is terminal actions, it's all the same. Next player, it's the same. And then I call it, because I like long names, I call it expecting minimax search, right? So rename some things. And that's going to be my entry point. I like to have entry points that I can recursively call at the same time, and it does something different. And in here, I call the to move and select among the maxes move, the mins move, and the chance move. Okay. All right. So here it's expecting max with all caps for max. That's max's move. I have expecting min. That's min's consideration. And then I have expectee expectation. I know, horrible names, right? And expectee expectation, it's going to compute the expectation over successors that are assumed to be min nodes. And then eventually what happens in the recursion, it bottoms out. And when it bottoms out, you return the utility. So ultimately, as you traverse downward, you're going to get utilities that you weight with probabilities each time you step back up to the expectation node or that call of expectee expectation. Does that make sense? Any questions? And so literally, this is like alpha beta pruning, only, you're doing a little bit nuanced difference. You're folding the call into min nodes inside of the expectation node. And when you're deciding whose action it is, it's between max and chance. And chance handles the min nodes for you. Right. But I still have different routines. Expectee expectation is going to call back to the expectimax and it's going to say, oh, I need to call up a chance node, a min node. So I'm going to drop in and call expecting min. Does that make sense? Because the chance is tied, or you could say you charge the min nodes to the chance, right? And you just treat them as two things, max and chance. Does that make sense? Any questions? No questions? Huh. All right, we can always get out early. All right. So think of these commonalities between you focus on expecting max. Once you get focus on minimax. Once you get minimax working, you literally copy and paste that code for alpha beta, and you're just adding that payload of alpha and beta and those checks to see whether you've improved the floor or the ceiling. Okay. And it's literally the same algorithm. It just has early stopping criteria on the search as you're recursing. Okay. And then for expectimax, you're changing the idea of what the non-agent zero entity is, and that's the chance node. And then you just say chance node when you're doing your expectation, you're going to assume that the successors you have are min nodes, which they always are. So you have this version or modification of alpha beta, remove the threshold checks, and then you add this third entity, the chance node, and then you alternate over consideration between max's move and chance's move, and chance just happens to on the side, called the min node. Does that make sense? All right. So think about the commonalities. It's really kind of beautiful, I think, between them. But the business end of this is in your implementation of minimax. So once you get minimax, the others are special cases of that code. And literally, you start with just a copy and paste of that code. Okay? All right. Is this helpful? Yeah. All right. So then last but not least, but wait, there's more, the better evaluation function. And this goes back directly to where we started last lab when we talked about this idea about material cost. In the classic maze and the mazes that are exercised in the test cases, you're going to have food pellets, okay? You're going to have Pac-Man, okay? You're going to have capsules. So back in the day, we called them power pellets, but I guess they call them capsules. Maybe copywriting is a thing, but nonetheless, think about the material cost. Now, we looked at all sorts of different material costs last time. We looked at the number of uneaten pellets. We looked at the distance of the ghost, and we had an evaluation function that had contributions of those two quantities along with the score. And the score decrements for each ply, right? Each ply for Pac-Man. And so here you'll notice something, and I'm not going to tell you what that something is, but the guidance I'll give and the hint and mind space I'll give is that look at every aspect of the environment, right? And look at the screen, look at everything that's there, because you're going to need more than what we used last time. Okay? Any questions? Because, for the life of me, I couldn't get full points, right? It was like one shy of that until I said, wait a minute, what else is there? And this goes back to what we said at the outset when we were finishing up the guidance or the mind space related to homework one, is that when you think about state, think about the relevant aspects of the environment. And so leave no relevant aspect unturned, and you'll get that last point, which end up doing. Okay? All right. Any questions about this? No questions? And so we've done, most of it, I realized, with the first evaluation function improvement, but this one's going to need some more. And it's going to require you just to look and think about every aspect of the environment, because what we did before doesn't cover every aspect of the environment. Okay. Any questions? No? No questions? All right. I certainly hope I'm recording. Yes, I am. All right. So with that, that's all I had. We can always end early. Have a happy weekend. We're like 25, 28 minutes early. So that's always good. All right. So if you have any questions, as usual, please don't hesitate to reach out on the Slack channel is preferred. I see those questions, some great questions back and forth. So thank you. And so, yeah, they sort of kind of slap you on the wrist and say, make sure you implement all your things you're supposed to implement. And they use an exception to do that. And part of that is making it so-called fail stop. The worst errors, if you ever look at performance testing as a discipline, are so-called Byzantine errors. It returns errors that are valid even though the computation is not correct. Those are really hard to debug, especially as your system grows in complexity. And the best errors to have are so-called fail stop. Your system breaks, it crashes miraculously miserable, and you see, aha, something happened right there. So even in your implementation, when you initialize something, initialize agent index to -1. It'll break spectacularly, but you'll see it when it happens versus returning a value like 0 because that's a valid agent index. And so they have this raising of the exception, which will break the autograder because they want to make it fail stop so that you are reminded very loudly that you haven't yet implemented part of the assignment, right? So Yeah, so that's a technique people use. And if you take performance testing and modeling, you'll learn stuff like that. So we'll stop there. I don't want to get between you and your weekend. I know for many of you, your weekend starts right after this class. So I'll see you all on Tuesday and I look forward to any questions that you might have. Let me stop.